Hey guys, today we are going to take a look at the derivative function. So this is really kind of what the essence of calculus is all about. It's all about the derivative. Okay? So the first question here is, what is a derivative? Now let's see. Let me just... So, what is a derivative? Well, I'm going to say the derivative of a function, so of f of x. So we start with a function f of x, and this is going to look very familiar. So we would say the derivative of f of x with respect to x. Respect to x. Okay. Let me zoom in so I can write a little neater. Is, and we would write it as f prime of x. Okay? You write just this little tick here to show that this is the derivative of the function f of x. Okay? And what it is the limit as h approaches 0 of f of x plus h minus f of x all over h. So you will notice that this is identical to the instantaneous rate of change formula, except that I'm using x's instead of a specific point. Now if I was evaluating it at that point, I could actually just sub in a number for x. But I'm going to show you what I mean by this with this example here. So given the function f of x equals x squared, we're going to determine the derivative at an arbitrary value of x. So what I mean is I'm not going to actually pick a specific value of x. I'm going to actually leave it as x. Okay? So what I'm going to have is I'm going to say f prime of x is equal to the limit as h approaches 0 of f of x plus h f of x all over h. So I'm going to sub this into the using the actual x squared, and we'll have that we've got the limit still. Remember, you have to write this until you're ready to actually calculate it. And so we'll have x squared plus h. Whoops, sorry, that's a mistake. Not x squared. Let's try that again. X plus h squared minus x squared over h. Okay? So we're going to have the limit of x squared plus 2xh plus h squared minus x squared all over h. So right off the bat we can see that this x squared and this x squared will cancel each other out. So I can now look, I've got 2xh plus h squared, but I've got an h on the bottom, so I can actually reduce all of those by 1, and I'm just left with the limit as h approaches 0 of 2x plus h. And of course, using substitution, we see that this is just equal to 2x. So the derivative of the function f of x equals x squared is just f prime of x equals 2x. So what does this tell us? Well, if we look over, we can say to determine the slopes of the tangents to the parabola f of x equals x squared, we can sub in these values of x, and rather than doing all that big calculation that we were doing before, we can just figure out what the slope of the tangent is just using this new function. So we say f prime of negative 2 is equal to 2 times negative 2, so negative 4. So the slope of the tangent of x squared at the point negative 2, or at x equals negative 2, is just negative 4. Similarly, we could say f prime of 0 be 2 times 0, so it's just going to equal 0. And finally, f prime of 1 would be 2 times 1, so it's just equal to 2. So the slope of the tangent at x equals 1 would be 2. So we can draw this to take a look and see what we mean by that. So there we go. We're going to have that and that. So we'll have, whoops, like that. And like that. So there's our parabola. There's our x squared. That's our f of x. Okay? So if we look, the slope of the tangent at x equals -2, well, so we're looking at right at this point here, the slope of the tangent, if we drew it like that, would give us -4. Now that's obviously not exact, but how I've drawn it there, but you can see that that is a negative tangent, and it is quite slope, and it works out to be about 4, or exactly 4 actually. But if we do the same thing at x equals 0, so right there, if we were to draw a tangent, you'd see we'd actually just get a horizontal line which has a slope of 0. And then finally, if we were to do it right here, I'll use green, right there, we can see that we would have a slope of 2. Okay? So that's what the derivative is used for. Okay? And this is the essence of calculus, as I say. So what I want you to do now is I want you to pause the video and I want you to complete this little investigation. Okay? Once you're done, come back and we'll pick it up. All right, so let's take a look at what the derivative tells us about the original function. Okay? So what it's telling us is the slope of the tangent, or the rate of change, at any point on the original function. So it gives us an equation to just calculate it easily. So we'll write, it tells us the slope of a tangent or rate of change at any point on the original function. Okay? All right, so that's what the derivative is then telling us. So we're going to discuss the existence of derivatives. So for any given function, you can't necessarily find the derivative at all given points. So what we say, that a function is differentiable. So a function is differentiable. At x equals a if f prime of a exists. Okay? So if we take a look at these examples here, we got 4 examples here, all of which the derivative does not exist at a given point. So if you look here, this point right here, much like these two are kind of the same idea, I can't draw a tangent to that point clearly, because I could draw it like this and just go through it and this and whatever. Like there's an infinite number of tangents I could grow. I'm missing the point, I realize, when I'm drawing those, but there's an infinite number of sort of quote-unquote tangents there that will pass through exclusively that point, no other point on the function. And because of that, we would say that it's not differentiable at that point. Similarly, this one here, you can see I've drawn a tangent to the point in the middle there, and it's formed a vertical line. If the tangent's vertical, the slope doesn't exist because it's a vertical line. There is no slope. It's an undefined slope, right? So the function would not be differentiable at that point. And finally, we've got a one here where we've got a jump there. And again, you can't draw a tangent to the function at that point because it'd be impossible. Okay? So those are some examples of functions that are not differentiable at a specific point. Okay? The other thing worth noting at this point is some other notations. Now, calculus is an interesting thing because it was developed at the same time by two different mathematicians, Isaac Newton and Leibniz is the other one. And as a result of that, they developed it at the exact same time, completely independently of each other, and so they developed two different notations for it. And we do still use both notations often. Generally, at sort of introductory levels, we use the Newtonian notation. So if we've got that y equals f of x, so we often use this one so if we take the derivative, this is the one that I've already used, we would write it as f prime of x. Now similarly, you could write y prime. Okay, and those are both Newtonian notations, and you do see them more at the introductory level. As you go on, you'll see more and more of the Leibniz notation, which actually, and I'm going to try and use both notations throughout, because you do need to get used to using both of them, because the Leibniz notation is actually kind of more convenient as you get into the higher level calculus. But the way you'd write it is dy over dx, and what we would say is dy by dx. Okay, and so this is telling you that we're taking the derivative of y with respect to x. Okay? All right, so we're going to take a look at this example here where we have the absolute value function. So the first thing we're going to do is we're going to graph it. Okay? So, the absolute value of x, we're going to go like that. And like that. Okay, so there's the absolute value. Let's just label it as f of x. Okay. So using the definition of derivatives, we want to show why this is not differentiable at x equals 0. So the definition of the derivative is that it was the limit of all that stuff. And so the reason this doesn't exist at x equals 0, and this is fairly straightforward when you, oh, what did I do? All right, well, this is fairly straightforward when you think about it, because as we approach this, so we're looking at this point right here. So as we approach from the left, okay, because it is a limit, right? As we approach from the left, it's approaching -1 because it is a constant slope. Okay, there's a constant slope there. It's -1 the whole way up to the point. So if you took the left-sided limit, you would get -1. If, however, we take the right-sided limit, we would get +1. And so at that point, the limit does not exist. And so this is why this is not going to be differentiable at that point. And as I say from earlier, you can tell just by looking at it, because it comes to a point, you can't draw a single tangent line to that point that is the only one that would be acceptable. Okay? Yeah, so the limit does not exist. Okay? All right. So example 3 is one I want you to do on your own now. Just take a look at it and try and go through it. And it's one that we're going to take up together at the start of the next class. Okay? So until next time, go Sabres.